This is very cool stuff. And there's absolutely no secular or evolutionary explanation for what I'm going to show you tonight. I'm going to give you a little window into the mind of God. How's that for an opener, huh? All right. A set is just a collection of elements, in this case numbers, that have a certain property in common. Now those sets are very easy because you can tell just by looking at the number if it belongs or not. You know if something's divisible by 2 or not, and you know if it's negative or not. It's got the minus sign in front of it. That's pretty easy. Some sets are a little more complicated, and you can't tell just by looking at the number whether it belongs or not. You're going to have to do a little bit of thinking first. And so we're going to spend our time talking about what's called the Mandelbrot set. And if that sequence remains small, then this number we're checking, C, is part of the Mandelbrot set. On the other hand, if the sequence of Z gets very large, then C is not a member of the Mandelbrot set. There we go. We tried 0, and we found that it did belong, right? We tried -1, we found it did belong. I won't take you through the tediousness of trying these other ones, but had we tried -2, we would find it does belong. Z stays small, but -3 doesn't belong. Z gets big. A half, positive a half, Z gets big, but positive a fourth, as Z say, you can't tell just by looking at the numbers. There's no apparent pattern. And we could do the same thing with the imaginary number. We'd find it does belong, and so does -I, but 2i doesn't, and -2i doesn't, but a half I does, and negative. There's no pattern that I can see. And so perhaps what we could do then is we could plot it on a graph, right, with the real numbers representing the real component of the x-axis representing the real component and the y-axis representing the imaginary component. And so all the numbers we checked, we'll color those black if they are part of the Mandelbrot set. So all the ones that are members, we'll plot those there. Those are the ones we checked, or could have checked, and they're black. And ones that are not part of the Mandelbrot set, we'll color those red. And so all these other ones, and they map there, okay? And so maybe it'll form a shape, and then we can see if there's a pattern, and it turns out there is. And so as we plot more and more of these, a pattern starts to emerge. And it's not a pattern you'd expect, but you see a pattern starting to form there? The pattern that forms is this. Isn't that strange? Not simple. You'd think, well, maybe it'd be a circle or something. It turns out to be an incredibly complicated shape. All this is a map of which numbers belong to the Mandelbrot set. Okay, so there's the coordinate with the coordinate system gone, so you can see the entire shape. And we're just going to spend some time exploring the shape, because the thing that I want to get across to you is this is not a shape that people made, right? This is a shape that is built into numbers. All this is a plot of which numbers belong to that Mandelbrot set. That's all it is. And it turns out to be wonderfully interesting. The upper portion here, you can see that this top sphere branches off into 3 branches, right? A stem and 2 branches, so 3 total. That's kind of interesting. The one next to it branches off, I don't know if you can see that, but it branches off into 5 branches. Can you count that? Can you see that? The next one, they're getting small, but it branches off into 7. And the next one, 9, 11, 13, 15, all the way, all the odd numbers, all the way down to infinity. Odd infinity, apparently. Whatever that means. On the other side, you get all the numbers, including the evens and the odds. Interesting in terms of the way they branch. Isn't that fascinating? So it knows how to count somehow, which is wild. And perhaps even more interestingly, 5 plus 3 is 8, yes? Right? And the little shape in between them has 8. And that's always the case. Whenever you check the bud in between 2, it adds the number of stems, no matter which one no matter where you're at. So again, 3 and 4 is 7. That's how many it has. 4 and 5 is 9. That's how many it has, and so on. So somehow it knows how to add. That's kind of neat. Well, let's find out. We're going to zoom in on that little thing. Oh, isn't that interesting? It's a baby version, right? It's the same basic shape as the parent. It's got the cardioid, and you got the little circles growing off of it. It's not identical. It's very similar, but it's not identical. It has extra spikes growing off of it. The parent didn't have these. They're very faint, but the parent didn't have these extra spikes growing off of it. So it is, and it's got a baby. Oh yeah, how about that? And of course, on the tail of that is another one. Let's see if I can go to that one. How about that? And you could do that forever, literally. And every time you get, we zoomed in on a spike, and the baby version has more and more spikes as you zoom in. So it inherits the property of the section of the parent that it grows off of, apparently. So all that on a tiny little section of a tiny little section of a tiny little section of the Mandelbrot set. And if you're wondering, there's nothing bigger. That's the ultimate one right there. There's nothing outside of it, interestingly. By the way, the colors are arbitrary. We can make those whatever we like. But the shape is something that God has built into numbers. That's what you need to keep in mind. This is not a human artist that made this. The computer helped us plot it, but the shape is built into numbers. This is just the shape you get when you plot what points belong to the Mandelbrot set. See the seahorses over there on the right side? They're upside down, and they're a little dark on this screen, but they really do look like seahorses. It's kind of amazing. So let's go off to the right here. We'll zoom in a bit on one of these seahorses. Now again, all you're looking at is a plot of which points belong to the Mandelbrot set, and it turns out to be wonderfully complex and beautiful. And I should point out too, remember the points that are very bright are points that are very close to being on the Mandelbrot set, but aren't quite on it. And so that tells you everywhere you see one of these bright points, it's actually close to a black spot that's actually part of the Mandelbrot set. It just gets so thin you can't see the black anymore. It's like a thin wire that wiggles around. It's just incredibly wiggly, you see. And in fact, mathematically, it's as wiggly as it can possibly be in 2 dimensions, if that means anything to you. Now, I found from experience, you can zoom in on the center of that till your heart's content and nothing really changes. It just keeps going forever. Little window into the mind of God. And I want to see what the threads of the spider web are made of. Yes? So let's zoom in to one of those. And they're made of more spider webs, smaller spider webs. How about that? And here you have you got the central hub of that spider web, and you got another one up there, and they intersect in the middle. And there's a little black spot there. Let's zoom in on that a bit. Oh, how about that? Isn't that interesting? And again, it's not identical to the parent. The main shape is, but it's got extra stuff growing off of it. We zoomed into a spider web, and it's got extra spider webs growing all the way around it, you see. And you might notice it's got a little baby version too. It gets computer intensive to zoom in too much though, so we'll go back out here. But all of that's in a tiny little section of the Mandelbrot set. That's what it is. Isn't that phenomenal? And again, I found you can zoom into the middle of that forever. And it just keeps going. It's infinite. And so let's go off axis and look at one of these strands to see what they're made of. And they're made up of, well, spider webs and more of these double spirals. And we have a new structure in the middle. I call them a bow tie. Doesn't it look like a bow tie right there? Kind of. So let's zoom in on that bow tie a little bit. And it's made up of 2 double spirals, and they intersect in the middle. And then 2 becomes 4. You see 4 in the middle. It's kind of a cross structure. That's kind of pretty. And then 4 goes to 8. Oh, you were expecting it this time, weren't you? Yeah. How about that? Once again, you got the baby version of the Mandelbrot set built into itself. Well, I wanted to see what else this thing has to offer, so let's zoom in on some other sections. Let's zoom in over here on this cardioid shape, and this they call the Valley of the Elephants. See the elephants marching along in formation, the trunk there, and it's all curled up? So isn't that interesting? We'll zoom in on the trunk here of this elephant. And this is a single spiral, not a double spiral, so it's just one strand. And let's zoom in on the threads of that. And again, you can zoom in, any spiral you zoom in on, you can zoom in on it forever, and it'll continue. We got now spider web type structures. We got single spirals, and now we have bow ties again, but now the bow ties are made up of single spirals. So it's interesting, whatever part you zoom in on, it kind of inherits the properties that you're zooming in on there. Is that not stunning? It goes from 2, and then in the middle there, you can see 4, and 8, and 16, and 32, and 64. See? And once again, you got a baby version built into it, so you can't escape that, apparently. Just remarkable. And just to think about what we're looking at. I mean, it's one thing to say, well, that's very pretty, but it's another thing to think about what you're seeing. You're seeing a map that God has built into numbers. Let's zoom over here on this valley. This is the one valley over, and they call this the Valley of the Scepters. It's an aspect of creation that we've only been able to explore in the last 30 years or so. Because even though it's been built into math from all eternity by God, it's only something that we've had computing power to be able to explore recently. You can zoom in, there's a cross structure in the middle, and again it goes from 4 to 8 to 16 and 32 and 64 and all the way into another baby Mandelbrot. Now that is all just a map. of what numbers belong to that formula. That when you plug the numbers in, they stay small, z stays small. That's it. It's that simple. And that made me think, what happens if you change the formula? What happens if we make it z cubed? You get a different shape. You get that. Instead, a little different. And so everything kind of gets duplicated. This type of structure that repeats infinitely on smaller and smaller scales is called a fractal. And this is one type of fractal. There are other types of fractals as well, but I find these to be really interesting. So z squared plus c gave us that shape. Z cubed plus c gave us that shape where everything gets kind of increased by 1. Well, you get kind of a threefold structure. Is there a pattern? You seen the pattern? Z cubed gave us kind of a double twofold structure. Z to the fourth gave us a threefold structure. Apparently the number of lumps there is the power minus 1. So it occurred to me if I made z to the seventh, I could get snowflakes. And it works. You do get snowflakes. How about that? And when you zoom in on the snowflakes, I'm not going to do the whole thing, but you get the same type of patterns. You get these beautiful spirals, and you zoom in long enough and you get more snowflakes. The same shape repeats itself infinitely. That is the nature of a fractal. And a fractal doesn't have to repeat exactly, it can repeat approximately. That's the nature of a fractal. When you can't tell what the scale is by looking at it, that's a fractal. Or a Koch snowflake. And this is where you add on a triangle. You start with a triangle and you add on a triangle to each side, and then you add on a triangle to each remaining side, and so on. And it gets more and more complicated. And you do it an infinite number of times, and you end up with this snowflake. And it's a very interesting shape mathematically. Mathematicians love to play with these sorts of things because it has a finite area. You can see it's only so big, but the perimeter is infinite. Okay, because it's infinitely wiggly, and so an ant could never possibly walk all the way around it, even though it has finite area. Or another way to think of it is if I could make a paint can that has the shape, instead of it being a circle, it has that shape instead, but it just extended out one dimension. That paint can would have a finite volume, but an infinite surface area, which means it could only hold so much paint, but it couldn't possibly hold enough paint to paint itself, which is just, that's mind-blowing to me. What conclusions can we draw from this? What causes the beauty that we see in these fractals? What causes the complexity that we see? The fact that they have these mathematical properties. Did the computer create the beauty? Did the computer create these shapes? The computer is like a microscope. A microscope does not create bacteria. It allows you to see bacteria. The computer allows us to see these fractals. Did people make it? Well, I mean, nobody knew about these until really the 1980s is when they were starting to, at IBM, they were looking at these things, and people were surprised by what they found. There's no way people could we can't make something infinitely complicated anyway. It's not like somebody sat down and said, you know, I'm going to make a heart-shaped structure over here, and then I'm going to put a bubble there, and an infinite number of bubbles, and no human being designed this shape. What causes the complexity in fractals? The fact that they have infinite complexity to them. Did the computer do that? No, a computer is not infinitely complex. In fact, most programs that will graph fractals can only zoom in so far, and then the computer crashes because it can't deal with the high precision numbers. You have to write special code to go in deeper than that. The program that I wrote for this will only zoom in a few billion times, and then it says, I give up. But the fractal goes on. It's beyond what the computer can plot. Yes, so the computer didn't create it. Did human beings create it? Again, we didn't sit down and design this, so we can't design things that are infinitely complex. Machines that human beings make get simpler when you zoom in. These things get more complicated. They get more complex as you zoom in. That's not a property of a human-made object. Did the formula create it? Z squared plus C. I mean, we did pick the formula, but what we found is it doesn't matter too much what formula you pick. There's built-in complexity to the numbers. Remember, we changed the formula, and you still get these beautiful, incredible shapes. So the formula didn't create it. The formula reveals a particular beauty built into those numbers, but it didn't create it. The complexity seems to be built into numbers, built into math. Were laws of math created by people? Well, laws of math are formulated by people. We invented the notation, that's why 3 looks like that. But we didn't create numbers. Numbers existed before people did, and laws of math existed before people did. As one example, the planets, the way they orbit the sun, they follow a particular law. They follow Kepler's laws, but Kepler didn't make those laws. He discovered them. Do they come from the universe? Now, this is a common one. People say, well, that's a property of the universe. But I don't think you can make that argument. For one thing, the universe is constantly changing. So laws of math don't reflect the universe. Now, there is a relationship between the universe and laws of math, and we'll get into that a little bit later. But you can't say they're created from the universe. In fact, 2 + 2 would equal 4, even if there were no universe. It's a transcendental truth, isn't it? It goes beyond nature. I'm going to say that laws of math stem from the mind of God. And so if you think about it, the properties, the existence and properties of laws of mathematics and properties of numbers make sense in terms of the Christian worldview. The person who says, well, there's no God, everything's evolved by chance, he's got a huge problem, because on the one hand, he knows laws of mathematics are conceptual. They exist in a mind. We know that. They're not something you can stub your toe on. They're not physical. They're mental constructs. But they weren't created by human minds, because they were around before human beings were around. And see, even secularists will acknowledge that. Of course, the planets orbited the sun perfectly fine before people. That law still worked. But they've got a problem because they don't believe in minds before human minds. Now, here's another interesting tidbit. Physical fractals. We've looked at abstract fractals, right? That exist only on computer screens after we map them. But their true fractals repeat infinitely and are only found in the conceptual world of mathematics. We can represent them with physical plots, but they only exist actually in the mind of God ultimately. But the physical world also contains many things which are approximate fractals. Snowflakes have a fractal quality to them, because it's not that they repeat exactly, but they have the same basic type of shape, that six-fold shape, no matter how much you zoom in on them. Ferns have a fractal pattern to them. The overall fern is the same basic shape as a leaf, as a leaflet, of a leaflet, and so on. It's the same basic shape. It repeats itself. I even found fractal broccoli, so broccoli is good for something after all. You see how it repeats it? Let me zoom in a little bit. You see, you got a cone, and it's made up of littler cones, which are made up of literal cones, and isn't that interesting? Wild. Coastlines have a fractal type shape. Now, these are the ones that don't repeat exactly, but they branch, and they branch into smaller branches and smaller branches, and so on. And so that has a fractal property. The way mountain chains look is fractal often. The way they branch. Clouds are often fractal. You can't tell, am I zoomed in on a really small section of a cloud, or am I looking over most of the sky? You can't tell because the same basic pattern repeats at smaller and smaller scales. The way lightning fragments is fractal. Is this lightning, or is it just a little spark? Well, in this case, you can tell only because there are buildings in the background. But if I did the same experiment with a little spark, it would branch the same way, pretty much. You can't really tell. And it's even cooler to watch it in slow motion. You can actually watch it branching out into that fractal pattern. Really quite stunning. So here's my question then. Why do fractals occur both in math, which is abstract, not made up of atoms, and the physical world, which is physical and is made up of atoms? Why do we have fractals in both? Same designer, yeah. That'll make sense of it, wouldn't it? So here we have a fractal that only exists in the abstract world of mathematics. You can't find that anywhere in the physical universe, but that one you can. They're very similar. Now this one, that's part of the Mandelbrot set. That exists nowhere in physical reality, but that one does. Isn't that interesting? This shape right here, it's called a Barnsley fern. You're probably thinking that's a real shape. It isn't. That's a mathematical graph. Yeah. And the entire shape, each of these leaflets is the same as the entire shape. And I'll prove that to you. Watch the entire shape here. It goes down and becomes one of its own leaflets. You see that? Yeah, let me do that one more time just because it's cool. Okay. Isn't that neat? So each one, it repeats itself infinitely. So that exists nowhere in the physical universe, but that does. That particular shape is a mathematical graph. It does not exist in physical reality, and this, unfortunately, does. This is part of the Mandelbrot set. It's one of those double spirals that we zoomed in on earlier. It exists nowhere in the physical universe, but that I've seen with a telescope. Isn't that interesting? You got fractals occurring in abstract and also made up of atoms. Why is that? And of course, the answer I'm going to lean toward is because God's mind is sovereign over the entire universe. Now, one answer that people might give would be, well, the physical universe obeys mathematical laws, right? So if something can occur in math, it stands to reason it can occur in the physical world because the physical world obeys math. And that's true, but it just pushes the question back, because now I'm going to ask, why does the physical world obey math? That's what I want to know. Why does the physical universe obey math? Well, in the Christian worldview, I can make sense of that. Mathematics are a reflection of God's thoughts, and the universe is upheld by the mind of God. So naturally, we'll see mathematical patterns in nature. It stands to reason in the Christian worldview. God upholds all things by the word of his power, and in him all things consist or hold together. Since God thinks mathematically about things, naturally the universe will be upheld in a mathematical way. The secular worldview cannot make sense of the properties of laws of mathematics, the fact that they're conceptual and yet existed before human minds, the fact that they're universal, apparently we assume they're the same everywhere, that they're invariant, they don't change with time, that they're exceptionless. We can make sense of those properties. That's consistent with the mind of God. And the secularists cannot explain why the physical universe is compelled to obey mathematics. But we can, because God is sovereign over the physical universe. It makes sense in the Christian worldview. The unreasonable effectiveness of mathematics in the natural sciences. He's trying to explore, apparently from a secular perspective, why it is that the universe obeys math. And what is his answer? It's difficult to avoid the impression that a miracle confronts us here, or the two miracles of the existence of laws of nature and of the human mind's capacity to divine them. It's amazing enough, he says, that the universe obeys these wonderful laws of nature. And it's even more amazing that they happen to be in nice, neat mathematical equations like E equals mc squared that the human mind can understand. It's remarkable. And his conclusion in the article is, the miracle of the appropriateness of the language of mathematics for the formulation of laws of physics is a wonderful gift which we neither understand nor deserve. He doesn't have an answer in his worldview. Isn't that interesting? He's a bright guy. So we've seen there's a secret code of amazing beauty and complexity built into numbers. That's what I want you to take away. Numbers have incredible beauty and complexity built into them. Maps of certain very simply defined sets, like z squared plus c, show infinite complexity and tremendous beauty when you map them on that plane. Human beings did not create the complexity in fractals. We merely discovered it. It was there all along. Computers did not create the complexity in fractals. They merely helped plot it. You could, in principle, do this all manually. It'd take forever, but you could. The intricacy of fractals is built into mathematics by God. That's the only explanation that makes sense. Fractals have no reasonable explanation in the secular or evolutionary worldview.